Here's problem 3027. Each of two parallel wires separated by 8 millimeters carries a 20 amp current. These two currents are oppositely directed. Determine the magnitude of the magnetic field at a point that is 5 millimeters from each of the wires. Alright, so let's try to visualize what's going on here. So we have two wires that are 8 millimeters apart. So let's put one on the x-axis here and one on the x-axis over here. We have them oppositely directed, so I'll have this first one coming out of the page and the second one going into the page. And we'll call this first one I1 with a current of 20 amps, and I2 is also 20 amps. Okay. We want to find the magnitude of the magnetic field at a point that is 5 millimeters from each of the wires. Alright, so we have 4 millimeters to the origin as I've drawn it, and if we're going to go 5 millimeters from the wire, we have to go 3 up this way. So here's our point P up here on the y-axis, such that we're 5 millimeters from this wire and 5 millimeters from that wire. So there's our point P. Now if I were to employ the right-hand rule for wire number 1, pointing my thumb out of the page towards you, then my fingers would curl counterclockwise, and so I'd have a magnetic field that's going around this as so. And at point P in particular, the magnetic field is going to be tangent on that circle. So this magnetic field, let's call it B1, will be tangent to the radius of that circle, right, like that. And if I'm looking at wire number 2 with the current going into the page, by the right-hand rule, there will be a magnetic field that's going clockwise around it. Something like this, and in particular at point P, it will be tangent on that circle, and let's call that B2. By symmetry, with the same currents and the same distance away, the magnitude of these two magnetic fields will be the same. So let's write that. B1 will equal B2 in magnitude, and that will be mu naught I over 2 pi r for both wires, and that's going to be 4 pi times 10 to the minus 7 times 20 amps over 2 pi, and we are 5 millimeters from each wire. So what does that give us? Let me go ahead and do this. The 4 pi divided by 2 pi will give me 2. So I have 4 times 10 to the minus 6 divided by 5 times 10 to the minus 3. And that gives me 8 times 10 to the minus 4 Tesla. So each of these magnetic fields is 8 times 10 to the minus 4 Tesla to begin with. Okay. We have to worry about these components. And let's imagine that we establish a line that is parallel to the x-axis like this. Now if I were to look at these angles, let's call this theta. Let's call the angle opposite theta in this right triangle here, alpha. Then this angle right here would also have to be theta. Alright? And then we have a right angle right here. So the complementary angle to theta would actually have to be alpha. So this angle of B1 with the x-axis, negative x-axis, is alpha. And I could do the same thing on the other side. If this angle here is theta, and its complementary angle here on this side is alpha, then this angle right here would have to be theta, because it's complementary for this right angle here. And then looking at this right angle here, the complementary angle to this theta, it will be alpha here. So the alpha is the angle that we have for both of these vectors with the x-axis. So I can write B1 as being equal to B times the negative cosine alpha I plus b sine alpha j. And if I look at alpha, which is this angle in this right triangle, the cosine of alpha will be the adjacent side 3 over the hypotenuse 5, so it will be 3/5. So this is going to be equal to a negative 3/5 b times I, and the sine of alpha would be 4/5, so this would be 4/5 b j Tesla. Alright, so that's b1. b2 will be equal to b cosine alpha I plus b sine alpha j, and so that will be equal to 3/5 b I plus 4/5 b j. We can see that our x components are going to cancel out when we add these two fields together. In other words, b, our net field, is going to be the summation b1 plus b2, and that's going to be equal to a negative 3/5 b I plus 4/5 b j plus 3/5 b I plus 4/5 b j. And we can see then that the negative 3/5 and the positive 3/5 bi cancel out. So we're going to have 4/5 plus 4/5, which will give me 8/5 b in the j direction. So that's going to be 8/5 is 1.6. So that's 1.6 times 8 times 10 to the minus 4 in the j direction. And 8 times 1.6 is 12.8 times 10 to the minus 4. So this is going to be 1.28 times 10 to the minus 3 Tesla in the j direction. So that's the magnitude of our magnetic field, 1.28 millitesla in the j direction. One way to visualize this, if I were to add these two vectors, tip to tail, so I have b1 going off in one direction and b2 coming off in this direction, then the summation of the two would be this vector here, which is totally in the j direction, is the two y components of those two vectors add together, and that is my resultant b vector in the j direction, 1.3 millitesla in the j direction.